FTM, and I do not remember correctly, but I will review for the exam, right? So let's begin with finite element method. Finite element method in 1D was studied. So let's briefly review finite element method in 1D. We break up the given interval in using basis functions having a certain height at a specific point. For instance, let's use a finite element like this, having 1 here, but 0 elsewhere, right? 0 elsewhere. Or let's consider an element having 1 here, but 0 elsewhere, and so on. Let's have a function like this, and so on. So we create many elements like this and name these things using phi1, phi2, phi3, and so on, and then phi(n). Then our goal was representing the solution using the linear combination of these things. Because the basis function is determined, the only thing remaining is the determination of coefficients, C1 times phi1, and then Cn times phi(n) is the solution to the differential equation. And from the differential equation, we obtain these C values using Galerkin method. In other words, we reduce the value to the minimum. And last time we covered this thing, and now we are considering two-dimensional finite element method. And once you understand two-dimensional, then you will easily understand three-dimensional. But we don't cover three-dimensional in this course. Then what is the similarity and the difference? Similarity is this thing. This mathematical representation is similar, but what is different? Basis function itself is different. Here, basis function is like this, right? So it's not very difficult to determine the basis function, but now we are handling finite element in different shapes, right? So assume that we have this kind of domain, then our finite element method have height 1 here, right? I will represent height here, height 0 here, height 0 here, right? Height 1 here, height 0 here, height 0 here. It's a plane and covering this triangle, then height 1 here, 0, 0 here. Of course, this is not the only finite element, but in this course, we will handle the finite element having triangles. It's the simplest, and there are many possible finite elements. For instance, it's possible to use a rectangle to create finite element method. So there is an advantage and disadvantage. Advantage is this: we can easily locate these things or position these things using index. But disadvantage is the shape of the domain that I will introduce very soon. So this has advantage and disadvantage. And we can even use multiple nodes like this. Inside one shape, we can use multiple nodes. Instead of just vertices, we may use more nodes to represent. So there are many ways of representing finite elements. And the finite element satisfies this condition. At one point it is 1, right? Height is 1. At other point is 0. It's like this. Take a look. This kind of finite element has 1 at this point, right? 1 at this point, and other points it has 0. At other nodes it has 0. And at one node it has 1, at other nodes this. Similarly, this finite element has 1 here, and at other nodes 0, 0. Do you follow me? Then, for one triangle, we may have 3 different finite elements. What is the next one? We have 0 here, we have 1 here. Or we have 0, 0 here, 1 here. So there are 3 possible finite elements. So you can already feel the pressure, right? It is not easy to implement these things compared to simple finite elements that we handled in one dimension. But we are not, I don't want to be too specific at this moment of overview, because I want to overview stuff and then later return back to this triangle and then let you know how to handle this kind of triangle in actual situation. So roughly, our finite element looks like this. Assume that we break up the domain, right? We break up the domain using triangles. So we use triangles to break up the domain. And as you can see, this has an advantage over the rectangles because we can break up the given domain using these kind of things without much problem. But let's stop around here. So assume that you break up the domain using small triangles. Then focus on this point, right? At this point, it has height 1, and then it has height 0, height 0, height 0, height 0, height 0, height. So you can imagine, right? It's like pyramid shape with more size, right? So at one point it has height 1, but at other surrounding point it has height 0. So if I try to sketch this thing in 3D graphics, then it looks like this, right? So at this point it has 1, at other point 0, 0, 0, 0, 0. So finite element looks like this roughly, right? So this is our, for instance, assume that this, we call this P like 5, right? P5 looks like this. And then P6 may look like this. Assume that you have something here, then it has height 1, and then other place height 0, right? Right? This kind of thing is P6 or something, right? So we can create finite elements at all points. So as you can see, theoretically it is nothing, but practically, especially when you try to implement, it's something, right? It's not easy. So finite element itself is not easy to implement. Of course, I will let you know about the details later, but roughly, we are using these kind of finite elements. So take a look. Finite element, for instance, P1 is the one having height 1 here. P2 is the one here. P3 is the one having height here. P4 is the one having height here. P5 is the one having height 1 here. P6 is so we create finite elements like this and cover all the domain. That's all we do initially without any theoretical stuff. Just we create finite elements having 1 at the specific position. Another knows 0 and elsewhere 0.
So is our domain, does that also have heights, or is it just like a flat domain and we're just making the basis function have heights?
Right. The domain itself is flat. Domain itself is flat. So on top of this flat domain, we create finite element having 1 here, and then other place 0. So we create one finite element. And then the next position, next node, we create the finite element having 1, and then other points 0. And then we create something, third one, and then having 1 here and then 0 here. So roughly, these are the steps. We first discretize the domain. We discretize the domain. Assume that your domain looks like this. Then, assume that your domain looks like this, then we discretize the domain using triangles. So better triangle is the triangle having regular shape. Close to regular shape is the better triangle than something that looks strange. So having domain having like some regular triangle is best. So we use triangles to break up the given domain, right? So you can use any triangle sets to break up, right? So initially we discretize. I will describe and later summarize. So first thing is discretization of the domain. In fact, in the past, I assigned homework problems like this. I gave some shape and then asked the student to discretize. And one student scanned my homework and then discretized, and then returned the file. I'm completely confused. What is the file having? So I gave the shape. The outer line was the shape that I gave, and a student scanned and then discretized using triangles, right? So assume that you're handling the problem, then you can discrete this using triangles. One can discretize. Of course, this is not the best. Why? As you can see, this shape is not close to regular triangle, right? Try to use regular triangle. I am not saying this is the best, but I'm saying that this is one way of discretizing. Then we have a function, like basis function, having height 1 here, right? Height 1 here, and height 0 here, height 0 here, height 0. So we have some shape like this, right? And then we have the next basis function having height 1 here, and height 0 here, height 0 here, height 0 here, height 0 here. Do you follow me? So having height 1 here, and height 0, 0, 0, surrounding points, right? Connected nodes has height 0. So we can create basis functions at all these points. So do you completely follow me up to this point? So you have a domain, then you discretize using triangles. Regular is best, but if you cannot, then discretize anyway. And then after discretizing, the second thing is find the basis function.
Regular triangles, you mean as close as you can to the same size?
Same size, right, sir? That's right. Then afterwards, we need to determine the coefficient, right? So solution is approximated by Galerkin method, and roughly ICN, right? We find these coefficients, right? Using Galerkin approximation that I will introduce very soon. Then afterwards, after determining C, just either plot or make a table or do something, right? Or do something to present your solution. Of course, you may give a bunch of numbers. This is the solution. So some engineer gave you the shape of your airplane using a bunch of numbers. Oh, height here is this number. Someone gave plotting. What is better? Graphics or table? It's up to you. So roughly these are the steps. So I will summarize one more time. First thing is discretization. Discretize the domain, right? That means we're using, in fact, in this case we are using triangles, but you may use different things. You can use these kind of shapes, you can use rectangular shapes, and so on. Second thing is basis function implementation, right? Basis function. Third thing is Galerkin approximation, determining CI, right? Galerkin. Then final thing is assemble the solution. Assemble sounds very sophisticated, so this is the reason why I don't want to be too sophisticated. I say, oh, just plot or write the function using the coefficients that you found. Roughly these 4 steps are required. So I will cover one step at a time, but mostly theoretical part is in determination of CI, Galerkin's approximation. So instead of covering other things first, I will cover these things today. And if you have enough time, you may cover other steps. But I will focus on this. someone makes the description unnecessarily hard by using this kind of word, assemble. Then suddenly, what is assemble? So let's do it. Assume that we have a given domain, and interior points basis functions are labeled this way. P1 function, having 1 here, right? 1 at this node and 0 at other place. P2 function and so on. So we somehow cover all the interior nodes, and then determine P, right? Any order you may choose, right? PP. So interior has P1 through PP. Then what about the boundary? Boundary also requires basis function. So PP plus 1, PP plus 2, and so on, right? PP plus 3. So all the way through we cover the boundary, and then PQ, right? We stop at PQ. So in other words, we have total Q basis functions, right? Q basis functions. Phi function 1 through P covers interior, and phi function from P plus 1 through Q covers the boundary. Then the solution should look like this. Solution should be C1 phi1, C2 phi2 up to CQ phi q. And determination of these C1, C2 is the crux of this method. But determination of CP plus 1 up to CQ is very easy. Why? These are determined by what? Boundary condition, right? Because we have the boundary condition, we can determine these surrounding points. So in this sense, we assume that these are known. Even if we use basis functions like this, these are known, right? By boundary conditions. So we usually use this kind of partial region, right? Assume that this region is R, then the boundary of R is represented this way, right? This round D expression and R. So round D, R represent boundary, right? So by boundary condition, we can determine this. So assume that our boundary function is given. For instance, sine xy. Then we can use sine xy result at the specific position to determine the value C, for instance, Q. In other words, at this point, we know the boundary condition. Then that boundary condition becomes CQ. Do you completely follow me? Then the only remaining stuffs are C1 through CP. Right? C1 through CP should be the interior basis function, right? The coefficients of interior basis function is required. Then from this point, I will show you Galerkin site. Of course, if I say Galerkin's, then you may think very strange, but we in fact did Galerkin's idea before. In one dimension, we already did the same thing. We have a differential equation like this. We have a differential like this, or F, right? We can make it F. We have a differential equation like this. Then, instead of using this one differential equation, we use what? This kind of differential equation with basis function, right? Interior basis function. And then, not just multiplying, integrating over the region R, right? Area integration, right? Over the region R. Then, how many equations like these are possible? How many total? P equations like these are possible because K varies from 1 to P. So total P equations like these appear. So once we solve these P equations, right, system of these P equations, then we can solve this for C1 up to C and CP, meaning we find the solution. So roughly this is it. So in some sense, in some very like short books, you may see this, then this is the end of the story. But I want to give you the details of handling these kind of things, but roughly the idea is this one. So it's essentially the same as one-dimensional case. You know one-dimensional case. We have set of equations like this, and we solve the system to determine C. Exactly the same. So I won't be very slow, and I want you to understand all these things. So if you have a question, you ask. If you don't, then I will mention about the easier version of this thing. Then let's do it. When Peter Lex came here, he mentioned about integration by parts. Similarly, we have three-dimensional version of integration by parts, or multi-dimensional version of integration by parts. So roughly, we can write this kind of integral using integration by parts. So we use the boundary of these things to get pk, and then integral of this thing. I will use this notation, and integrate this thing over the boundary of R following the R. So this is the one. We use integration by parts, and then we differentiate the other. So we differentiate this one, and then attach this one. So this is the integration by parts, or more precisely, Green's first identity. Of course, people who took Calculus 3 knows this very well, right? Green's first identity. Roughly integration by parts, right? We have two functions multiplied, then we integrate this function to get this one, and we differentiate the other function here, right? So this is integration by parts. Or more precisely, Green's first identity. Then, on the boundary, what happens? On the boundary, pk, interior functions are all what? Interior functions are all what? 0 on the boundary, right? So the differential equation becomes very simple. The differential equation becomes this. O minus R delta pk delta u dA equals the right hand side f pk dA over R. Or we can mix these things on the same side, right? We can mix these things on the right hand side. So roughly, this is it. This creates many equations, right? Why? Because we can replace u by the sum of, so we can replace this u by because I use the carriers different index Cj, right? Right? So we can differentiate these things, right? We can differentiate these things using this thing. Then we have many terms here, but all these things can be handled. So essentially, this is the system that we can create and solve. So please browse these things and ask questions. Why? Because U is the linear combination of basis functions, right? And now U is replaced by these things. And eventually, this goes in, right? This goes in. So eventually, this will go in. Then, roughly, we will have gradient of phi, gradient of phi k, gradient phi j, multiplied many times, right? Multiplied many times with c. That means if we can integrate gradient, multiply gradient over R, we can essentially create a system. So theoretically, it's not tough.
Would you reiterate the difference between the del R and the R again?
The boundary. So it is R, right? This is R, right? And this is boundary. Boundary. Any questions? Then I will move this thing to the right hand side, or I will rewrite this equality. If I rewrite this equality, then we will have this form. Then as you can see, P times Pk can be easily handled, and phi k times, this gradient pk times, this gradient pj can be handled easily too. That means we can create the system very easy. So I will show you the system. In fact, I don't even have to mix two things together. I just write these things and I move this back to the other side. I'll move this back to the other side. Any questions? Then let's call this AKJ, and let's call this BK. Do you follow me? I will call this AKJ. K came from this, J came from this, right? I call this AKJ, and I call this BK because then what do you have? You have AKJ multiplied by CJ equals minus BK. Or you can call the whole thing BK. It doesn't matter. Not very tough. Then what is this? If we write this thing in system form, it is this. J running from 1 to P, right? So we have system. C1, C2, CP equals B1, B2, BP. And this thing has a J and J are the same, right? So A11, A21, one, two, one, three, and so on. A1P, right? And then A21, A22, A23, and A2P, and generally A P1, AP2, and then APP. So roughly, what we have is a linear system, and if you know how to determine these coefficients or the right-hand side, then you can create a system to solve for CI. That means we can find the solution by just using this CI by assembling these numbers with the basis function. So I will pause, and then you may check whether you completely understand everything up to this point or not. So what is AIK? It starts something like this, right? Something like this. But as you can see, if they are not adjacent, right? For instance, assume that we are handling P1 here, and then P9 here, and they are very far apart. Then this and this multiplied together will become 0, right? Right? The gradient of this and this multiplied together will become 0. The only gradient that survives is inside this region, right? Surrounding rectangles, it is okay, right? So P1 is non-zero. Inside is surrounding rectangles, right? But outside the surrounding rectangle, the function P and gradient P is all 0, right? In other words, this kind of matrix is not very dense. It's very sparse matrix. Many are zeros. Many are zeros. For instance, if you have 10 and 1, as you can see, 9 and 1, then it becomes 0 because they are far apart. So this is the overview. This is the end of overview, because after this, we will jump into actual calculation and derivation and formula creation. And that part may make you confused with the theory stuff. So I want to separate that kind of detailed part with the theory part. The theory part isn't necessarily difficult. So it's almost the same, theoretically almost the same as one-dimensional. So one-dimensional FEM, two-dimensional FEM, three-dimensional FEM, all these are very similar theoretically. Practically, they are very different. Practically. Why? Even basis function creation is tough. So I will assume that you completely understand this and then continue. But if you still want to stop me, stop me. Then it's time to mention about the details. And I will mention about details until 2:55. And after 2:55, I will take a break and then cover for the review for the exact.
One more quick question. Since we X'd out that integral with the boundary, do we ever have to consider, I mean, it doesn't, I'm sure we do, but it doesn't look like we have to consider the boundary conditions anywhere. Or is that inherent in one of the basis functions and I'm just missing?
Boundary function. This part is 0. On the boundary, this interior basis functions are all 0. So 0 multiply something, integrated is 0. Look at the basis function. At the boundary, basis function is 1, right? But at this point, at the boundary, the function value is all 0. So we multiply this function with others. Then on this boundary, this 0 kills all the terms. So all these things become 0 on the boundary.
Yeah, maybe if we do an example, I'll see it better.
Right? So assume that you have two functions. assume that you have two functions. So this is the first function, f. This is the first function, f, right? And this is the second function, g. So what is f times g on the boundary, on this boundary? If you multiply f and g on this boundary, f times g is what? At this point, 0. And then at this point, what? 0, because of this boundary. So up to this point is 0. That's what I meant. So on the boundary, this function is 0. So you integrate to 0 multiplied by something on the boundary. Then what happens? 0, right? 0 multiplied something is 0. But, right. So we handle the boundary coefficients using boundary conditions. But the interior function, coefficients should be determined. But on the boundary, this pk is 0. So pk, 0, right? This is like a boundary function having 0, right? This is interior function having 0 here. Multiplied to anything becomes 0, right? So f times g is 0. Integrated is also 0. Any other questions? Then, now, you need to calculate the double integral, right? So I will let you know how to handle double integral. So from this point on, it's not theory anymore. It's practical calculation over and over for various cases. So essentially, so this is the thing that we covered, and I mentioned that akj is nothing but the integral of this function right? And bk is, this is the summary. So in some sense, you don't even have to know about the derivation part. Just the calculation of these things are enough. I just rewrote what you did in the next, right in the last note, right? So we may encounter many, many cases. I am covering the easiest case, but assume that you have more complicated differential equation, then we may encounter various cases. So I will cover the triangle idea. And assume that you have a triangle in two-dimensional plane. Say it has x1 position, y1 position, and x2, y2 coordinate, x3, y3. Then we consider a plane having height 1 here, right? Having height 1 here, height 0 here, height 0 here. So we are considering this kind of plane. Then let's check whether you have good intuition or not. Can you find the center of mass of this triangle? What would be the center of mass of this triangle? Your intuition says what? Right. So averaging x coordinates and averaging y coordinates will give us the center. Right? The center of mass is called x bar, y bar, can be easily determined by this. X bar equals x1 plus x2 plus x3, and average value of this thing, right? And y is similar, right? We can find the center of mass. Why do we care about the center of mass? Because we will use two-dimensional midpoint rule. In one-dimensional midpoint rule, midpoint is obvious. In three-dimensional, in one-dimensional midpoint it's obvious, but in two-dimensional midpoint rule, what is the midpoint? Midpoint is this one. So we will use midpoint approximation. And technically, people call this barycenter. In any case, we use this barycenter, right? Then the next thing is this. Can you find the area of this triangle? Very easy. You create the vector from this to this, and vector from to this, and then what kind of a product give you the area related thing? What kind of product? There are two products in vector. Great. Cross product gives us the area of parallelogram, right? So cross product will give vector. So we want to find the area, and people wrote down these things in matrix form. So the area is given in this form. How will you define the determinant? Determinant D is written this way. We attach 1, 1, 1 for convenience, and x1, y1, x2, y2, x3, y3. Then we can find some value. This is the determinant, right? So we can find the determinant of these things, and area can be determined by this determinant. Area of the triangle, area of this triangle equals, this D could be plus or minus, right? So D is a plus or minus with parallelogram, so we have the size, then we have the area of the triangle. If you want to verify, calculate the cross product and compare the result. So area of the triangle is found, and if you have doubts or questions, ask me. If you even want me to derive, then I will derive. But you don't have to spend time on this kind of derivation stuff, because we are covering computational science. We are not covering triangle calculation or vector product. So is this okay or not? If you don't think it's okay, then ask me, and I'll derive it. But it's trivial, right? So assume that you have, so to test it, let's make a triangle. That's the best way. So easy triangle is a triangle like this. Oh, assume that we have a triangle like this. 0, 0, and then 2, 0, and then 0, 1, right? This is a triangle, and you already know the area. So please calculate the determinant D and then find the area of this triangle. Of course, by intuition, we can find the area like 1. But please check your determinant value with this. You should attach 1, 1, 1 on the left-hand side, and then position. Any order is okay. Any order is okay because we use absolute value. So do you get the area? in this case, it's obvious, right? But assume that the rectangle has very difficult positions. So I will arbitrarily pick some function like this. Assume that you have 0, 0, and somewhere here, right? Somewhere like 2, 7, and somewhere like 8, 3. So find the area like this. Find the area of this one. Then it's not easy, right? Without the formula. As soon as you find the solution, please let me know. Did you find it? What is it? 20 what? Great. So 25 is the result. I will show it. .25 is the area. So once you have a triangle, you can use it. Especially when you have opportunity to teach at some secondary schools, you may say, oh, I can find the area very fast, and they may doubt what kind of things you have in your head. Then just listen in your head, right? Get this in your head, and then you can do it.
Yes, some of them are asking what that is.
Excuse me? Oh, in your head, you should be aware. You should not show this. In any case, area finding is done. Now, the next question is this. It's not very difficult to determine it, but assume that we have 1 here, height 1 here, height 0 here, height. This is not the coordinate, but height. Height is 1 here, height is 0 here, height is 0 here. Then, at the very center, right? At the very center, what is the height? What do you think is the height? It is like middle school geometry.
1/3.
Great, it's 1/3, right? Why? It's proportional, right? It's proportional. 1, and then going down 1 time, twice, and 3 times to reach, right? To reach the bottom. So it is 1/3. The height here is 1/3. 1/3, right? Not just here. Following this parallel line, right? Parallel line, 1/3, right? And following this parallel line, 2/3, right? So it is 1 here, and then 2/3 here, and then 1/3 here, and then 1/6 here, and so, right? So you can guess the shape, right? It is, what is it? I don't know. Let's forget it. In any case, maybe 1/2, right? 1/2. So height can be easily determined, right? Do you follow me? Because it's plane, right? It's plane. We have 1 here, then going down, 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 and then going to 0, right? Then you might wonder, what kind of function can represent this kind of plane, right? This kind of plane in this triangle. Can you find this plane? First of all, what should be a pattern of the equation of this plane? Planar equation should be found, right? What is the equation of this plane? Generally, equation of the plane in 3 dimensions is what? Thank you. Great. So, you generally we can write the height by using this kind of equation. Generally, this kind of thing creates piece of something, right? Piece of something, right? So let's say piece of 1 having, so I will describe the situation. x1, y1, x2, y2, x3, y3. Then having height 1 here, having height 0 here, having height 0 here, right? So we are describing this plane, and then let's call this P1 inside this triangle, A plus BX plus CY. Then, can you find A and B and C, A, B, C? Can you find A, B, and C or not? By using height information and point information, can you find A, B, C? If you can't, you may review the book Linear Algebra in not the full linear algebra, but like 111 or something. So we can find A, B, C by using Cramer's rule. When did you learn Cramer's rule? About pre-calculus, right? So using Cramer's rule, you can determine A, B, C. So let's do it. So assume that we use x1 and y1, right? Assume that we use x1 and y1. Then it becomes A, bx1, and then cy1, and then by this condition, it is the height is what? Height is what? 1. And phi1, x2, y2 is, by this definition, what? 0. And similarly, 0. Then you have 3 equations and 3 unknowns, right? We have 3 equations, 3 unknowns. Then we can determine these things for A, B, C, right? So I will write this in matrix form. In matrix form, we have this 1, 1, 1, and then x1, x2, x3, and y1, y2, y3, and then capital A, B, C equal multiplication equals 1, 0, 0. So using the Cramer's rule, you can determine capital A, capital B, capital C. So let's determine A, B, C. Capital A equals, by Cramer's rule, 1, 1, 1, x1, y1, x2, y2, x3, y3, and this A is, this column related to A is replaced by this thing. And then x1, x2, x3, y1, y2, y3. Then because of this, we defined this previously, right? This is the area of the parallelogram, right? Parallelogram. And this is x2, x3, y3 minus y2, x3. So A is found. Please find B and C. Please find B and C. I did the easy one. Please find B and C. Using the Cramer's rule, please find B and C. So if you didn't get these things, then let me know. I just apply the Cramer's rule to determine capital A, capital B, capital S, meaning I now know how to determine the equation of the plane. Before determining this equation of the plane, I just used rough idea, right? It has height 1 here. It has height 1/2 here. It has height 1/3 here. And it has height 1/6 here, right? And it has height like 2/3 here. It still has height like 5/6 here. But this is not good enough. We want to know the equation at every position. And yeah, I'm very interested in the value of this function at very center. So please theoretically prove that at the very center this has height 1/3. Please verify it using the formula. Please verify it whether this has really 1/3 there or not. Not by intuition, but by rigorous proof. So please prove it. I will use maple to simplify this part. So this is the result, right? This is the result. And I will divide this by d. So let's calculate d. d is equal to 1, 1, 1, x1, y1, x2, y2, x3, y3. Then, but nothing but the calculation gives us, I will subtract first row from the second and third row. So first row subtracted gives us first row. And I will subtract the first row. And the first row subtracted. And then because of this, it's nothing but x2, x1, y3 minus y1, and then minus y2, y1, and then x3, x1, right? So nothing but just linear algebra, right? I calculate the determinant, so I will divide this thing by this determinant, right? So I will call this result numerator, right? Numerator. Numerator is this one. And then I will define the denominator. Denominator is x2 minus x1 multiplied by y3 minus y1 minus y2 minus y1, x3 minus x1. So we define the numerator and the denominator. Then I will define the numerator by the denominator and then simplify. 1/3, right? So as you can see, this shows why mathematics is difficult. Usually by intuition, we know the height 1/3, right? But mathematicians need to prove this kind of thing. In the past, they didn't have Maple. So they should hand calculation to prove this. In any case, we now completely define the function inside the triangle. And x1, y1, x2, y2, x3, y3 are generic. In other words, you can call any position x1, x2. I mean x1, y1, right? You can call any position x2, y2, and so, right? So x1, y1, all these are generic. In other words, you can program these things to find the equation of the plane at any position, any triangle, inside any triangle. So if you don't have any objection, then I will cover the next part. But if you have a question, ask me. So phi is completely determined by this that you calculate using Cramer's rule. So in any case, I'll hide this calculation part and then write the result, because you see the result. You saw the result, right? It has 1/3, right? I really calculated this result. Then the next thing is this one. We are seeing this kind of thing frequently, right? Right? This kind of thing with appropriate index, right? But that one is not just the first one, it is generic, right? So we can just find the gradient of this one. What is it? What is the gradient of this one? By definition, partial derivative of that function with respect to x is the first component, right? And then second component is partial derivative of this with respect to y. So what is the partial derivative of this function with respect to x? It is 0 plus b plus 0, right? Because we differentiate this with respect to x. And if we differentiate this with respect to y, 0 plus c, or simply bc, or bc are defined here, right? bc are defined here. In other words, by this, you can handle all the cases of what? Gradient pk multiplied by gradient pj, right? Theoretically. Because it's nothing but the dot product BC of this type and then BC of the next type, right? Multiplied together. Any question? Yes?
Why are we calculating the P bar? Why did we do that?
Oh, just checking whether our function is really the function that we wanted. So it's not very important to verify. The next thing is this one. We see a lot of integrals like this, right? We see a lot of integrals like this. So this f is not specific, so I will use different character. So I will use just something very strange, right? So I will use the strange h function, right? The strange h function is not just one specific function, but generic case. Assume that we have this kind of thing inside a triangle, right? Inside a triangle with x1, y1. x2, y2, x3, y3. Then, I will not prove it today, but I will write the rule, midpoint rule to find, right? You know about the midpoint rule in one-dimensional integration. In one-dimensional integration, using the midpoint, we can find the integral. Similarly, inside this triangle, using the midpoint, we can evaluate the integral. That's the one we will use. So this integral becomes the midpoint used. What is the midpoint? Very center is the midpoint, right? Very center is the midpoint multiplied by area of the triangle, right? Area of the triangle. I used the T. This is the one. Then what is the error? Order of h squared, where h is the maximum distance. So h is the maximum distance. H is the maximum distance between 2 points inside this triangle. So h is the, where I will describe it. Where h is the maximum distance between 2 points. Between 2 points, x, between 2 points, just between 2 points, between the 2 points inside the triangle. So assume that we have this as maximum distance, then that kind of maximum distance squared is the error. It means what? If you use smaller triangle, then our midpoint rule, our midpoint integration will have pretty accurate integration results. Do you follow me? So don't use two big triangles, right? Because if you use two big triangles, this error could be large. But if you use small triangles, like 1/10, then 1/10 squared order, right? The error is not very big. So up to this point today, I cover, and then afterwards, I will review for the exam, and you may ask any questions about the past stuff other than this. If you complete on this, you don't have to return back. So let's take a break until 3 by point information, all the necessary derivative information, right? Derivative information such as y primed of times 0, y second derivative of times 0, y third derivative of times 0. These kind of things are given, then it's called initial value problem. And Euler's method is, of course, you can return back to the summary and see it, but roughly finding the slope at the given point to shoot, and then you may use the next position to find the next point. And RK4 is using these kind of things and determine the values. And two-dimensional one is doing these things in x and y, or x1 and y1. K-dimensional one is using these things for k dimensions. And so the differential equation can be handled by converting it to system, to a system, right? To a first order system. First order differential.
Is that all you want us to write down on the test?
No, you should write down the details. So for instance, sometime before, some students said, what is the method, Newton's method? Oh, it's a method of finding root. And then what is the bisectional? It's the method of finding root.
I understand you can then for an order one is take like an example of either a second order or a third order and convert it into a system of first order equations. Is that what you want?
Well, nth order, and then you can just dot, y1 is converted to, I know, so first derivative is y2, third y3, and so on, and then describe.
Okay.
So you should not say, oh, Euler method is a method used to solve differential equation. And roughly up to this point is obvious, and if you have questions up to 6, ask me. And the shooting method is the method converting the boundary value problem into initial value problem, because we cannot handle boundary value problems directly. So we convert the boundary value problem into initial value problem by attaching some guess, right? In other words, we have y of 0, but we don't have y primed of 0. So we guess y primed of 0 and shoot, and then if we overshoot or undershoot, we adjust and then reshoot and reshoot until we have reached the target. Collocation method is a method similar to mathematically or technically looks like just linear combination with basis functions, right? It looks like that, but in calculation of these coefficients, we use point height, right? Point information. In other words, we evenly divide the points, and then using height information at each point, we can determine the unknown coefficients. And finite difference method is the method using y1, y2, yn, representing the unknown heights, and then we create a relation between them and then solve the system. And finite element method is the method that I explained today, right? On-dimensional versions. Then the next one is this one, and you either use gamma expression to explain it, or you can write the formula if you want. So I will return back to the notes to find these steps. But before covering that problem sets, I will review what we did. So take a look. So I explained the gamma location last time, and here I used these three things. This all means the order of accuracy. Assume that in the spatial direction we use delta x. Then the error is less than some constant times this delta x to the power of n. This means order is n, right? Do you follow me? Order is 2. It means the error is bounded by c times the delta x squared, right? That is the meaning of the order. So order 2 means if you have small delta, like 1/100th, then 100th has the error less than what? C times 100th squared. That means 1/10,000, right? 1/10,000 multiplied C accuracy. So this kind of thing is the meaning of the order. So essentially, if we use small numbers, we may get better results, but I will explain some bad stuff later. And stability restriction is sometimes known and sometimes not known. And stability, I used S to represent the known stability restriction. And CFL stability restriction is the theoretical one. The domain of dependence should be included in the domain of numerical dependence. That kind of thing is developed. But unfortunately, CFL stability restriction is not a sufficient condition. It's a necessary condition. In other words, if we somehow find something satisfying CFL condition, it doesn't guarantee the stability. It only is required to be stable, but it's not the condition that is guaranteeing the stability. Do you understand what I mean? So it's necessary condition, but not sufficient. In any case, let's consider advection equations. Then we are using function with time variable first, and then spatial variable x, and then t and x, and then y and so on, right? Then Euler method is the one having forward advance and then center difference. And in formula I wrote it. Then in this case, people try to find the stability condition and they failed. So it's unstable. So it's unstable. Of course, even if CFA condition is satisfied, right? Even if CFA condition is satisfied, it doesn't guarantee the stability. And backward difference has accuracy of order 1. In other words, what is the error if we use this backward difference? The error is some constant times delta x. So if you use small delta x, then error is not very big. And there is no limit, no restriction. You may use any size. But what is the problem? If you use big size, then the error will increase, right? If you increase delta, then the error will increase. Even though itself doesn't have a limitation, the error increases. And the CFR condition is none. The next thing is Crank-Nicholson. And people prefer this one because of one reason that you can obviously see. What is the advantage? Among three things in the set, what is the...
Can you go backwards and say that it's always stable, or the second order?
Backward, do you mean?
Well, if you taking Crank-Nicholson off the page, you can't see it.
Oh, sorry. I somehow...
But the interesting is it's always stable in the second order.
Right. Always stable and second order. So mostly second order is the greatest advantage. And then there is no limitation. But also there is drawback, and I will explain that kind of thing after introducing this, because last time we didn't have enough time to explain some theoretical stuff. But at least I'm just reviewing now, and on the exam, you either write this representation or this one. So it's your choice. Or you may develop your own and then say, explain your notation and let me. And leapfrog method is one with second order and this kind of thing. And upwind method is this one. And box method averages differentiation. In other words, this itself is differentiation, right? F or C or B represents differentiation. So it is differentiated, but it is averaged, right?
That's like Crank-Nicholson, but averaging both.
Right. And Lax method is a little bit awkward. We usually stop here in Euler method, right? But we consider second order derivative. It's like Taylor series with just first term or the next term, right? And Lax is very strange form, right? But there are many, many things. And we have heat equation. And as you can see, once you have second derivative, we have a clear winner. Right? C squared, right? C squared is clear winner. We don't consider other things. And this F can be converted, right? F can be replaced by B or by average, right? By average. And we can even use Crank-Nicholson idea. So Crank-Nicholson is done. Any questions?
The ones that were Lax were those Peter Lax?
Yes. So his contribution is amazing. Many of you met him or saw him, right? And leapfrog is very similar, and box in 2 dimension. I mean, heat equation looks very strange. You may change these numbers and insist that you can have better results. But in any case, this is known to be best in this situation. And Laplace equation has this kind of pattern, right? It's obvious, right? And then you can solve this for this term, right? This term. Then you can use SOR or something. And there is no restriction. But as I mentioned, it's not the restriction of the differential equation, but last time I briefed, of course I was notes to explain. If we have somehow some bad situation, the solution cannot converge, the result cannot reach the solution. Somehow it cannot pass some kind of barrier in between. That means you should go up to the solution, but somewhere there is a barrier, and then it comes returning back, and then back, and then you cannot go up. Then you cannot find the solution. So that kind of thing should be avoided. Not because of the limitation here, but because of error in numerical steps. And wave equation is the one like this. Wave equation is the one like this. And this is the stability condition. and higher order dimensions. And roughly, when you add one more spatial variables, then we divide by the number of unknowns. For instance, if R is equal to 1/2, and we have two variables to 1, then you may divide it by 2, then it is 1/4, right? That can be used. So roughly we covered all the cases, and I will briefly mention about the limitations. Theoretically, when we divide the interval by very small numbers such as delta x, it should have better result, even though time consumption is more, right? But people really investigated this problem and found that it's not the case. In other words, small delta x doesn't mean it's very nice. It's not. So it's like this. There is a trade-off. So delta x equal to 1 is bad, and delta x equal to 0.1 is pretty okay, and delta x equal to like 0.01 is very nice, and delta x is not better than this result. In other words, somehow this could be the best, and this is not the best, right? These are not necessarily the best. So strangely, if you use very small delta, then the result may be worse than the previous result. So somewhere in between, there might be best result, in fact, because we investigate these things among these four. This might be the best, but somewhere in between, the best result might exist. Then why? I explained this before briefly. The reason is this: when you use finite difference method, we use this kind of approximation. And as I mentioned before, if you use big H, then itself is already far away from the actual derivative. If you use big H, do you follow me? If you use small h, then what happens? The truncation error and all sorts of error happens, error follows. So either way, we lose, right? If you use small h, then we have a truncation or computer system error. If you use big H, then it's not close to the derivative. So in any case, it was already embedded. Because of this reason, when you use FDM, try to find the optimal delta x instead of dividing it by like 1 billion, divide it by a reasonable number that you can easily recognize. For instance, if you have some kind of shape, then you check how many points can represent the stuff without losing resolution. Then you may think, oh, about 2,000 points might be enough. Then you use 2,000 points. If you think about 500 might be enough, then use 500. Do not divide by too big a number, right? So this is the idea. So people really examined these things and wrote a paper, survey paper doing these things, right? So they picked some problem and solved the problem using varying delta x, and then presented the result. Amazingly, like delta x equal to 0.00 like 5, 6 might have, I cannot remember exactly, but had the best result. It had the best result compared to smaller number of delta x. So up to some point, small delta x is good, but if it's way too small, then these things happen. So that's the limitation of our method. Another thing is this one. When you have a differential equation, we have this kind of situation, right? This means what? Implicit method, right? So, for instance, Crank-Nicholson or backward Euler has this kind of situation. to determine y sub n plus 1, we need to know y sub n plus 1. So when you have this kind of situation, we should predict the height, right? We should predict the height using known straightforward method, right? Known exact method. And then afterwards, after filling necessary positions, we iterate, we run it. That's the drawback, right? Because even though it doesn't have any calculation or stability restriction, we need to really rotate and rotate many times, right? So this has a drawback. So roughly, yn plus 1 is determined by some explicit method or explicit step. After this, you iterate. So yn plus 1 determines yn plus 1, and new yn plus 1 determines yn plus 1, and so we iterate. And then we check the difference between the previous iteration and the next and done, and you may determine when to stop. So this kind of thing is a drawback. So for instance, backward different or a Crank-Nicolson method has this kind of drawback. So when you code is tougher than the straightforward method such as Euler or upwind. Any question?
We go back to that PDE sheet that you had up for a second. Yeah, stop right there. If you're doing a problem such as the E equation, you've obviously got 4 or 5 different methods to solve. Is there any particular criteria that you use to pick one?
Usually in this area, people prefer Crank-Nicolson because it has second order accuracy and there is no big stability condition. So with nice delta x such as for instance 1 over 500, right? With nice delta x, you can iterate these things to get pretty nice result. Right? Then your result is almost close to the real solution.
It looks like the same thing could be said for the leapfrog, and it looks like it has fewer calculations that would need to be done. So what would be the benefit of the Crank-Nicolson over the leapfrog?
Because usually straightforward method, the explicit method, handles the derivative at the next previous position. So usually, I will write it in the next page. So this is the situation. When you solve differential equation, we have the slope information here and slope information here. But slope information here is used to determine this point, is Euler idea. But in general, slope information here may not be even close to the slope information here. Because we use the slope information here, our approximation is already wrong. But that kind of Crank-Nicolson thing smoothen this. In other words, by using this idea too, you may have better result than the straightforward. So in other words, leapfrog or upwind method use this kind of just one determination, right? But this is calculated at this position to get the better slope information. So usually backward method is developed and used because of this reason. So when you need to really find a nice final result, it's a good idea to use Crank-Nicolson stuff, right? So that you can get the order 2 accuracy result with small delta x, right? Delta x could be 1 over 1,000 or 1 over 500. Then it's pretty nice, and then you determine the delta t appropriately, right? And then run it to determine the. So this time is for you, so ask questions. If you don't have a question, you don't have any reason to be here. So ask questions. Oh, even this kind of thing was questioned. How how do you implement the animation? And I recycled some ideas from your return, and then roughly plotting it for time, right? When time equals to 0, we create first frame, right? First snapshot, right? And time is equal to 2, we create another plot, and then we pause a little bit to see the previous plot, and then next plot, and so on. So just this idea. And in surface area, in 3 dimension, instead of just plot, you may use surface stop, right? Surface stop to create the plotting, and then you plot and plot and plot each time, for each time frame. Of course, there could be different ideas, so you may pick any idea, because this course is not the course covering programming techniques. Programming techniques are covered in maybe CS 101 or something, right? I don't know the course number. And in fact, I saw these kinds of things before. When we solve differential equations, we have a domain, usually rectangle, right? Domain given in rectangle. And inside this domain, we use position x, y. And we use index to represent the same position. For instance, we use ij or jk or something, right? Then you should convert position to index or index to position, right? So you should do these things, no matter what domain is given. If you don't do, then you may have strange situation in your program. If you want the actual formula, then I can do it. It's not very difficult. It's like middle school stuff. So it's not very difficult. If you have questions, you can ask me, then I will do it for you. But it's the obvious thing, right? You can convert the xy point into ij index. So roughly we covered all the steps necessary, but strange thing is this one. I will return back and then check the homework 7. It's not for homework 7, but at least because it's a wave equation. If you central differences, then delta t over delta x could be 1, right? Then roughly 1/2 should work, right? But somehow it had strange situations. I will check this part.
At least it goes for me. When I cut the delta t in half, it all worked out nicely.
I see. I see. I will check. Yeah, I will check why it is happening, so I will check that right. So please check your notes and ask questions. If you don't, then you may leave the room, or you may ask questions personally about coding or stuff